All right, welcome everybody to another beautiful day in Amsterdam at the Complexity School on Climate Change. I'm very excited that we have Detlef van Vuuren as the opening keynote today. Detlef leads the Image Integrated Assessment Modeling team at PBL, which is the Dutch Environmental Assessment Agency, and he's a professor of Integrated Assessment of Global Environmental Change at Utrecht University. Detlef had a key coordinating role in the development of the RCPs, the Representative Concentration Pathways, and the SSPs, the Shared Socio-economic Pathways, scenarios heavily relied in the IPCC reports. He's basically the rock star of climate science mitigation, okay? He has published twice as many articles as the years have passed since the Industrial Revolution, and has been named the 4th most influential climate scientist in the world. So please, Detlef, take it away.
Okay, thanks. Do I share my screen in the right mode?
Wait, I think we missed you, lost you. I think we missed you, lost you.
You lost me?
One second.
We said, yeah, following up again.
Okay. Okay. This needs to be.
Can you hear me?
Yes.
Okay. Funny. I had to switch on the monitor and then the sound came.
Very good. Okay. I think, can you see us?
I can see you, yeah. And can you see my slides?
Yes.
Okay, great.
All right. Please take it away.
So Fabian already introduced myself. I'm Detlef van Vuuren. I'm working at PBL and Utrecht University, but most of the time I actually work for the IPCC. Here on the right, you see us as IPCC authors at an approval session from an IPCC report. On the other side, where you can't see, there are 180 countries that need to approve the report. This is actually at night where we're trying to defend the report after a question. Yeah, so these reports are important because we try to help policymakers in different countries to formulate right climate policies. And it's important as well because we know that climate change is already happening. By now, the Earth is about 1.5 degrees warmer than it was in pre-industrial times. And we also know why it's happening, because of greenhouse gas emissions. And unfortunately, the greenhouse gas emissions are related to almost everything that we do. And so they are related to the energy that we use, the goods that we take from industry. They're related to the way that we live, to how we transport ourselves, and the food that we eat. And so if we're going to go to zero emissions, what we need to do to prevent climate change, we have to change everything that we do. And we have already promised the world that we want to do that, because in the Paris Agreement, we have indicated that we would like to stay well below 2 degrees and preferably 1.5 degrees. And yeah, key questions are obviously what would be needed to meet these goals, how can we achieve it, and what will happen if we miss it. And that this is not an easy question because more or less it is equal to asking what will happen in the future. And if we look at that question, and specifically in the context of climate change, we have to understand the full causal chain of climate change, which starts with human activities, and those lead to energy and land use, which by them in turn are related to greenhouse gas emissions, and which lead to higher greenhouse gas concentrations in the atmosphere, to climate change, and finally to impacts. Yeah, understanding that full chain means a lot. And we somehow need to know something about population in the future, about technology, about political changes, the elections this year in the US, and how will that play out and how will that influence choices that we make, the policies that are formulated, also how environmental problems themselves impact, again, population growth, for instance. But not only that, we need to know this on different scales. And decisions here in Europe might influence maybe bioenergy use and therefore maybe land use in South America. We needed to know this for different time periods. If we build a coal plant now, it's going to stay for another 40 years. Or if we put a CO2 molecule in the atmosphere, it influences climate for centuries. And then all of this is inserted in as well. And then at some point, it becomes a little bit too difficult to understand this all with our own brains. And therefore, computers can help us to understand how this works, model-based scenarios. And this is the topic of my presentation. And so we try to describe this whole chain of climate change with computer models. And one part of that is the human system, and one other part is the Earth system. And a set of models that we can use for this are integrated assessment models. And those describe the interaction between the human system and the Earth system. In the human system, we need to say something about energy and land use. And in relation to that, projections for population and economic activities, technology. And in the Earth system, we need to describe climate change itself, but in relation to biogeochemical cycles, to ecosystem dynamics, pollution. And then the interaction between those systems are mostly the emissions and land use, but also the feedbacks from the Earth system back to the human system. And these are called integrated assessment models because they integrate the human system and the environmental system. They also try to integrate across different issues, maybe biodiversity loss and climate. And these models are called assessment processes because they are there mostly to support decision processes. And so they're a little bit too difficult for normal science, but they are absolutely relevant. And so it's not trying to absolutely know something, it's just to assess possible futures. Now, how do you fill these models? You can try to look into historical evidence. Here, for instance, I've plotted income versus meat consumption, and you can, all the dots are countries, and you can see that there is some relationship between income and meat consumption. If people become richer, they at first start to eat more meat, and at some point there seems to be some stabilization as well. This is the historical relationship, and so we can use that to potentially use that in the model as some evidence of how things could develop. But we also have then the opportunity to say, okay, actually in this particular case, I assume that something happens that is different from the past. But having these relationships of how the past behaved give us some starting point to think about the future. The same for energy use. Here, it's income versus energy use. You see, again, that there is some relationship. You see also that there is spread. All the red dots are different countries. So we can have a standard development pathway where energy use goes up if you increase income. But there are also different pathways. The dot way up is the United Arab Emirates, but also US is way above the curve. On the other hand, Japan at a similar income is way below the curve. And so there are choices that countries can make and that determine whether we go for a 3 times energy intensive future or a third of that. So if we are describing future systems, we need to describe different layers. And one layer is the layer of physical entities. So things like the natural system, but also infrastructure, things that we can touch. And the nice thing about those physical entities is that we have natural law how to describe them. And that's really helpful in models because we can simply start from basic principles. But that's not the only thing that we need to describe about the future. We need also describe the second layer of social behavior, of economic reality. And here at that layer, it's rules, it's laws, it's behavior. There are observations of behavior of people, but they're not necessarily always true. They can change. And so that's the second layer of things that we need to describe. And then there's a third layer of things that is behind that as well, which is the layer of beliefs, and culture, and that influences the choices on the second layer. So if we describe these future systems, we have to describe all those different layers. But that also means that for the bottom layer, but also to some degree for the second layer, models are useful. Because we have these physical laws and we have these observations that can help us to describe that system quantitatively. But at the slightly higher layers, it's a bit useless, because it's really hard to describe cultural change in numbers, or to describe certain behavioral change in numbers. And therefore, we also use storylines to describe the future. Sometimes words are simply much stronger to describe the systems than numbers. And that means that if we are making scenarios about the future, we use these two systems. We use models where we have strong empirical evidence, quantitative evidence, and we use simply stories about the future where that is not available. And so it's a combination of narratives and modeling where there's enough knowledge to define quantitative relationships, and narratives where there's a need for complexity and flexibility. And then with these scenarios, we can explore different futures, which is useful. We can see what happens under different assumptions. But we can also try to map out things that are not likely, that are not useful to consider in your decision making. It's not easy. This is a newspaper I found myself about 20 years ago when I bought my house, and it was below the carpet. And so somebody put it there. And it's actually, this newspaper says, it's from 1972, nuclear power is going to push out oil and gas in Dutch. And if you read the article, it says that nuclear power is going to be so cheap in 2000 that it's even too cheap to meter. And so it will be available for free. And therefore, all that oil and gas that the Netherlands has needs to be used before that time. Otherwise, it becomes worthless. And so the experts advise the Dutch government to really start using that oil and gas heavily. And that's what the Dutch government did. And the Dutch government, in response, tried to attract as much heavy industry into the country as possible. And that's why we still have this very high heavy industry. What happened in reality is the following: that blue part is natural gas, that purple part is nuclear power. And so nuclear power did not expand at all in the Netherlands. In fact, it became much more expensive. And so by now, people are not investing in nuclear power anymore, simply because it's a very expensive way to make electricity. So the wrong prediction influenced the energy policy of the Netherlands to try and sell out our natural gas and to avoid getting stuck with it in the ground. And so it's not easy to make projections about the future. These people were completely wrong. And therefore, partly making scenarios and making alternative stories is a useful way to possibly deal with that. Yeah, and we do that with using different types of models. We're describing the Earth system and the human system. And so you can think of models that describe that Earth system in a complex way or in a simple way, and the same for the human system. And so then we can just differentiate different types of models. We have Earth system models, which are these complex natural science models that describe the Earth system in a very complex way, but hardly have any description of humans in them. On the opposite side, we have models like computable general equilibrium models. These are economic models that are rather complex in the description of the economic reality, but have hardly any Earth system in there. And so then we have these models that try to compromise these integrated assessment models, that have some description of the Earth system, some description of the human system in a medium complex way. One of the example is IMAGE. That's the model that we're developing ourselves at PBL, which is an integrated assessment model with a relatively complex Earth system and a medium complex human system. But there are other models, integrated assessment models as well. This is actually a paper from a PhD student that was working with me, and defended her thesis last year, Lisette van Beek. And she was looking into the history of integrated assessment models. And that history more or less starts with the publications of the Club of Rome, when in 1972, when they published the calculations with the World 3 model, limits to growth, and tried to show that endless growth would lead to problems with respect to resources. And at some point we would have used up our resources, and at the same time with respect to pollution. And that was the first time that people were using computer models to warn society, this pathway is not something that we can sustain forever. A few years later, the energy crisis started, and people started to really work on energy system models to do similar projections and to see what alternative futures would be possible. Yeah, and then in the early 1990s, late 1980s, the issue of climate change appeared, and people started to develop these integrated assessment models for climate. And then those became actually quite successful, and they are now still an important part of the IPCC reports. I can also show that by specifically looking at that period, 1990 to 2015. And here with the blue bars over that period, we have analyzed how important integrated assessment models are in the IPCC report, in the subsequent assessment reports. Yeah, and over time, we actually see that there is some increase in the importance that IPCC attaches to the use of integrated assessment models. So again, we are talking about model-based scenarios, and I've already emphasized the role of uncertainty by showing that example of the nuclear power, but there's at least another important factor, which is values. And so this is a conference that we organized already 15 years ago at PBL, when we were doing a sustainability outlook, and we invited Dennis Meadows. Dennis Meadows is behind that 1972 Limits to Growth report that I mentioned before. And we invited Rijn Willems, who he is speaking to. And Rijn Willems was the CEO of Shell at the time. And they are having this conversation, and Dennis Meadows is emphasizing, maybe in 1972 I indicated that there was a problem with unlimited growth. But now in 2005, I'm actually even more worried. I think that a crisis will happen within the next 10 to 30 years if we continue like this, because we run out of resources. And then Rijn Willems answers by saying, but you were looking at the wrong thing, Dennis. You actually don't realize how there's another factor, which is human brains. And human brains are not limited. We can invent actually new technologies and therefore have more efficiency. And therefore, these problems that you're talking about, we can solve them. We have always solved them. And so two different people, two different views about the future and how to deal with it. And then we are using scenarios. And I think that if we realize that there are these two important factors, one is uncertainty, and that's the horizontal axis going from certain to almost unknowable. And then there's this other factor about actually values and whether we agree on theory or not. And we can realize that there are these different tools to explore the future. If we agree on theory and we are almost certain, and then we're in a world of facts. If we, on the opposite side, completely don't know the system and also disagree about values, and then everything becomes speculation. And then we as as scientists, we can be part of the debate, but we don't have anything important to offer compared to other people. But there are these in-between situations, predictions. We can use that for systems that we can do testable experiments. We can predict the weather because we can do this experiment over and over again, and we know the system and therefore can say something about that system with a certain amount of certainty. Scenarios we use in a situation with even less certainty, and where we can, under what if situations, can say something about the system, and most of the time we can't even indicate how certain we are about the future, but it is something to possibly reckon with. And so we have different words to indicate how we would like to look into the future. And my talk is about these scenarios. And I'm going back to that scheme that I showed before, this causal chain of climate change. And that's the chain that we would like to describe using these computer models and scenarios. And there are actually all kinds of actions that we can take as humans to try and deal with climate change. We can deal with impacts by adapting to climate change. And so if there's sea level rise, we can build dikes. We can also try to deal with climate change itself by geoengineering. One of them is techniques is called solar radiation management, where we put particles in the atmosphere to scatter incoming sunlight. We can also try to take greenhouse gases from the atmosphere. That's called carbon dioxide removal, for instance, by planting trees. The other option is to remove emissions at the stack of a power plant, carbon capture and storage. We can try to mitigate climate change simply by increasing efficiency and using technologies that don't emit CO2. And then there's the option, obviously, of changing our activities. We can stop eating meat and therefore reducing greenhouse gas emissions. So there are these options, and it is for policymakers important to know what kind of portfolio of actions might be attractive to take. One important factor here is that we have divided our science into different silos. And we have a group of people that studies the climate system from a physical perspective. That's in the middle, and that's the climate system research. And then we have a group of people that looks into mitigation research and looks mostly in this relationship between human activities and emissions. And then we have a group of people that looks into impacts and the impacts of climate change. You can also see it in IPCC, because we have this working group 1, the climate system research, working group 2, the impact research, and working group 3, looking into mitigation. So actually, one other reason why these scenarios are so important for climate change, it's one of the only tools that connects all these research communities. And the same scenarios are used in these research communities, and that's why we can actually bring that information together. Now, I would like to say something about the scenarios that we have developed. And when we were doing that, we thought, let's start from the very end and let's start from impacts. And if you think about impacts, there are 2 major factors that determine how worse an impact can be. And just, for instance, compare the Netherlands and Bangladesh and think of sea level rise and how it impacts those 2 countries. And it's, on the one hand, the sea level rise itself that is important, but just as important are the socioeconomic conditions. Is a country able to adapt to climate change? Is it able to build dikes because it has the capital to do so, or the knowledge to do so? And so, equally important, climate and socioeconomic conditions for impacts. And realizing that, we said, okay, if we are going to develop scenarios about the future, let's build a scheme where those 2 factors play a role and try to simplify that system again, because it's complex enough. So now we built a relatively simple structure for scenarios to support climate research. And so this is the matrix that we used. On one axis, we have the level of climate change, going from a lot of climate change. We add 8.5 watts per square meter of radiative forcing to the atmosphere, which is more or less equal to increasing the temperature by about 4 degrees over this century. And on the other hand, 1.9 watts per square meter, and that's equal to about 1.5 degrees of warming. This is one axis. And then the other axis are the socioeconomic conditions. I have no access there yet. I'll come back to that in a second. And this allows us to study climate change in different ways. And we can look into one column and see what is the difference between a world that goes to 4 degrees or to 1.5 degrees. But we can also look into these horizontal rows and compare how different developments in socioeconomic terms at the same level of climate change also determines our impacts. And so we have a nice scheme to study climate change. But in order to do that, we have to make that horizontal axis also operational. And we thought, okay, in doing that, we introduce a second matrix. And that matrix is related to climate policy. And I have earlier indicated all kinds of climate policies that people could have. But maybe the most important forms of climate policy are adaptation and mitigation. And if you then think of worlds where it's maybe difficult to adapt or easy to adapt, and worlds where it's relatively easy to mitigate and relatively difficult to mitigate, and then maybe we have something that is useful again to take into account in thinking about the future. And so that's what we did. We said, okay, there can be worlds where it's easy to mitigate and easy to adapt. Think of a world where maybe there are a relatively low amount of people that are collaborating with each other, that are relatively rich and that have a lot of technology. And that's a world where it's relatively easy to adapt and relatively easy to mitigate. The opposite situation can, of course, occur as well. If we have a world with a lot of population, high population growth, and where people are not collaborating but competing with each other, where they don't share technologies, where they are relatively poor, and then it's a world where it's relatively difficult to mitigate and difficult to adapt. You can also think of all kinds of other combinations, and maybe in a world where people, part of the population is relatively rich, but a large part of the population is poor. That part of the population would find it really difficult to adapt, but the richer part of the population, in theory, could mitigate. And then we create this SSP4 storyline. And so we thought of all these combinations. And with a group of people about 10 years ago, we developed narratives, stories for each of these possibilities. And they were published in the literature and reviewed as well. And they are quite similar to what I described now. The next thing that we did with these stories is actually trying to translate them into parameters that can go into models. And so we translated them into population pathways together with a demographic group at the IASA. We described them in terms of technology and developments and technology preferences, and gave that to integrated assessment modeling teams. We also described how potentially policies might be different in these worlds. And so from the storylines, we could make consistent sets of assumptions that could be used in these complex models. And these complex models need to make assumptions in all kinds of issues, for instance, land use, and for instance, energy. But because the storyline gives a consistent set of consistent description, it is possible to make a consistent set of assumptions both for land use and for energy. Yeah, so just to give an example of how this is done, this is an integrated assessment model again, where we have an interaction between a human system and an Earth system. It's actually the integrated assessment model image that we are working ourselves on at PBL. And so we can start to work with assumptions on population and economic growth. In this case, we get the projections for population based on the SSPs, these 5 different stories about the future from a team at the IASA. And we work together with the OECD to make 5 income projections. And we, in our case, take those as inputs into our model. And then we use that to run our energy model and our agriculture model, and to make projections about energy use. And we do that in quite some detail. We use the economic projections and population projections to make projections on 26 world regions for transport. That's shown in the top, where we make projections for using of cars, using of airplanes. Then we translate that into an energy demand. If we know how much cars are used, we have a description of what kind of cars these are, based on the choices between different cars. And then we know also what kind of energy is consumed. Part of that is electricity. And so we have a detailed electricity model. So to finally end up with a projection of primary energy supply. We can do the same for land use. In the end, we get 5 different descriptions of how the world could develop, in this case, for primary energy use. And as I indicated, we can do that for land use as well. We do that actually quite detailed. We have a map of 5 by 5 minutes, about 25 by 25 kilometers globally. And we model land use and agriculture demand. And if we then combine those projections for energy and land use, we can easily calculate also the impacts for greenhouse gas emissions. And that's shown here. And that's done in the model as well. And we can feedback then feed the greenhouse gas emissions into a small climate model and even calculate then the impacts of climate change back on energy use, like air conditioning demand, or on agriculture systems and the crop growth of different crops. And there are lots of these interactions in the model. Yeah, so that's how it goes in the integrated assessment model itself. But the scenarios are also used in climate research. And there we actually give the energy projections to climate models, that large-scale climate models, and that calculate also the impact of climate change. So in the next part of my presentation, I would quickly like to indicate the possible consequences of climate change given these scenarios, but also to indicate a little bit how we could prevent climate change from happening. And this is from the synthesis report of IPCC that was published last year. So here we have the SSP2 scenario, and the SSP2 scenario was the one in the middle. It's the medium scenario. It takes medium population growth, and medium economic growth, medium technology projections. We deliberately also developed a scenario that was in the middle. And what we have done as well is that we made a database of climate policies worldwide. And if we then introduce all those climate policies on top of this socioeconomic pathway, we end up with the orange line. And so climate policies worldwide are slowing down, luckily, the increase of greenhouse gas emissions if it would have occurred as was the case historically. They slow them down, they only stabilize them. There's a lot of uncertainty as well, as you can see by the in the areas around that orange line. But if we want to know what the climate consequences are of such a scenario, we can run these climate model parts of the integrated assessment model. We can also run these complex climate models. But one easy way is also to simply use this graph that was already published by IPCC. And in this graph, you see on the horizontal axis cumulative CO2 emissions. So the amount of CO2 that we put into the atmosphere. And on the vertical axis, the temperature that is a result of that. And this graph is actually made by running a lot of complex Earth system models. And what you can see is that there's a clear relationship with the amount of CO2 that we put in the atmosphere and temperature increase, but there's also some uncertainty. On the top of this area, we have some models that are more sensitive, and on the lowest end, we have also some models that are less sensitive. And the area is drawn up by the uncertainty in the climate models. Now, what we can do now is to calculate the amount of CO2 that is emitted under current policy, which is equal to the area under the graph. and fill that in the graph on the right. And then you can estimate how much climate change would occur. And in this case, you can calculate that it's about 3,000 gigatons of CO2 emissions, additional to what's already emitted today, which leads to a warming of about 2.5 to 3.5 degrees Celsius by the end of this century. Yeah, that is considerably more than we have promised the Earth in the Paris Agreement. Well below 2, preferably 1.5. It's also something that would lead to quite substantial climate impacts. Again, this is also from the IPCC report, where we have mapped risks of climate change against temperature. And these are different risk categories that are indicated on the low side. And you see risk increasing from very low, white, to very high, purple. Yeah, in a 4-degree world, or sorry, in a 2.5 to 3.5 degree world, we are in high risk for all these categories that IPCC looked at. And so this is something that we would like to avoid. This graph is also from the synthesis report of IPCC. And I think it's one of the most convincing graphs ever that IPCC generated. And what you see is the time from 1900 to 2100. And then historically, the temperature increase indicated from blue, low, to, what is it? Very purple, dark purple, very high temperatures. And then you see this historically increasing, and then you see also from 2020 onwards what the scenarios are indicating for further increase. And then it's related also to generations of people, people that are already living on this planet and that will experience climate change. And the different rows on the right side of the graph indicate the different scenarios, the different options that we have as humans, going from very high, and that was this scenario that I was indicating before, that has very high population growth and economic growth, to a scenario where we have climate policy very low. I come back to that scenario later in my presentation. But what you can see is that in all cases, the world will be much warmer than it was historically. And we tend to think about climate change as something far into the future, but the point of this graph is that it's not. It's something that we will experience, whether we're young on this planet or already grown up. Most of us will experience this high temperature during this century. Yeah, coming back to that slide that I had before, the one that was showing the different impacts categories and the cumulative CO2 emissions versus temperature. So we were in a world that was going to go to 2.5 to 3.5 degrees, and that was not the world that we had promised. So the question is, can we potentially avoid that? And so what is needed to stay within the Paris Agreement? And we can use that graph that I had before to then calculate how much CO2 we can still emit. And that's not a lot. And for well below 2 degrees, if you read that graph, we can emit above more or less 1,000 gigatons of CO2. Now, if you know that we are emitting 40 gigatons CO2 each year, this is about 25 times what we emit in a single year. For 1.5 degrees, we could still emit about 400 to 500 gigatons of CO2. These are the numbers in the IPCC report, but you have to realize that IPCC gave those numbers from 1st of January 2020. And so that since then, we have emitted another 160 gigatons of CO2. And that means for 1.5 degrees, we now have about 250 gigatons of CO2 left if you want to stay below 1.5 degrees. And that's about 6 times current emissions. And so within 6 years, we would have, if we continue to emit the current emissions, we have completely exhausted that carbon budget. So the bad news is there's not a lot of carbon budget left to stay within those temperature targets. I can also illustrate that by going back to my current policy graph. And because the orange line was the current policies, the purple line here is the line that you have to follow to stay within the carbon budget of well below 2. And the cyan line is the one that you need if you want to stay below 1.5 degrees. They have completely different trajectories of the current policies. They go down very rapidly. And you can even calculate if for the 1.5 degrees, if we have 6 years of carbon budget left of current emissions, it means that you have to go in 12 years to 0 if you want to stay within that budget. Yeah, 12 years from now, that is like 2036, which is really fast if you want to go to 0 globally. So luckily, we have a little bit of a trick left, which is negative emissions, taking CO2 from the atmosphere. There are different ways to do that. We can reforest the planet, but we can also use bioenergy and then capture the CO2 and put it on the ground. That's also going to take out CO2 from the atmosphere. And there's also something called direct air capture, where you take CO2 directly from the atmosphere and store it underground. There are a few other things. The most important thing that you need to know about this is it's maybe helpful, but it will not be unlimited, simply because it will lead to a temperature overshoot by itself, by definition. But also, most of these techniques are not unlimited. There's a certain amount of forest that we can create on this planet. There's a certain amount of bioenergy that we can produce. And there's a certain amount of storage potential where you can put CO2 on the ground. And so this is a couple of hundred gigatons of CO2 that we might be able to have as something extra on our sleeves, but it's not endless. And that means if you tell the models, find the solution that stays below 1.5 degrees, the models are going to use those negative emissions as well. And this is the solutions that they find. And so the purple is staying well below 2. The cyan is staying below 1.5 degrees. And with my quick calculation, I already showed that for 1.5 degrees, you need to be somewhere before 2040 at 0. And with these negative emissions, you have a little bit extra, and therefore the models actually indicate that around 2050, reaching 0 would be consistent with staying below 1.5 degrees for CO2. For total greenhouse gas emissions can be a little bit later. And that's also what the IPCC said. The IPCC said 1.5 degrees, we need 43% of reductions already by 2030 and net 0 around 2050. For well below 2, net 0 can be around 2070, but only if we start to reduce emissions rapidly now. If we don't, we go really, really fast with this 40 gigatons of CO2 through the carbon budget. And then actually that net 0 year needs to be much earlier. And for total greenhouse gas emissions, the net 0 year can be slightly later than for the CO2. Yeah, in that figure, and there's also in the middle one, an indication of not only current policies, but also the promises that countries have made. This is called the national determined contributions. And there's a little dot there that you can see in an uncertainty bar. But if you focus on the dot, that dot is way above the lines that are needed for well below 2 and 1.5 degrees. We call that the emission gap. And that's still, that's the current challenge. Can we convince countries to make even more promises to reduce emissions? So how are we going to get to 1.5 or 2 degrees? Yeah, we can use the models again, and then the models can introduce a combination of actions to go and find pathways that stay below 1.5 and 2 degrees. And these combinations of actions are efficiency improvement, using other technologies, windmills instead of coal plants. They can have that negative emissions that I introduced before, and they can reduce the non-CO2 gases. So there are lots of actions in those models, and they can show us pathways that potentially lead to something that is consistent with 1.5 degrees. So in the IPCC report, you find graphs like this, where we have here on the left emissions according to the scenarios without climate policies, and then on the low side you find scenarios with climate policies. And yeah, you can then plot the cumulative CO2 emissions versus all kinds of actions that are potentially in these scenarios. And so if you have the horizontal axis, cumulative CO2 emissions, then if you go from right to left, and you go from more or less 4 degrees warming to 1.5 degrees warming. And then you can see, for instance, in that graph on the top right, that if you're moving from high temperature scenarios to very low temperature scenarios, and that the renewable energy component of those scenarios need to increase rapidly. And so models are indicating that much more renewables are needed to stay below 1.5 degrees. And the models can help you by finding out how much more renewables, because it's then this trade-off between efficiency, non-CO2, negative emissions, and renewables. If we then look at a little bit more in detail to this, we can see that there's this relationship, but that models disagree a little bit about how much of each technology is needed. On the left side, actually those abbreviations stand for different models. And you see that some models indicate that a lot of solar power is needed to stay below 1.5 degrees. And some other models indicate, well, it's not a lot of solar power, it might be wind power. And so there is uncertainty among the models. And yeah, this graph is made by Mark Becker, who is in the room as well and is working in our team. And so the question that we tried to find out was, how robust are the messages of the integrated assessment models? And to do that, we made this graph. And this triangle indicates on the top the result that you find for a certain technology is mostly determined by the climate target. On the top, on the left, on the bottom left, the indication is it's mostly determined by the model. We have so much uncertainty that if you look at a certain parameter, the outcome is mostly determined by the model. And then if you look at the right, it says the result is mostly determined by assumptions. And so the model assumptions are in there, and we can identify a certain technology, and the findings for that technology are mostly determined by assumptions. I've already plotted in one dot, and this is the dot for coal use without carbon capture and storage. And what we know is that the amount of coal that can be used is strongly determined by the climate target. We can understand that. The amount of CO2 that is associated with coal is very high, and therefore we have to get rid of coal if you want to reach a certain climate target. And what Mark did was doing this decomposition for all kinds of technologies. And what we found out is that with some robustness, we can say a lot about how much fossil fuels can be used, which is little. And we can also say quite a bit about renewables as a group, or carbon capture storage as a group. Models find it still very difficult to distinguish different types of technologies. And so some models like PV, other models like wind, other models might be actually in favor of nuclear power. And so if you look at individual technologies, and that are these small dots on the left, the bottom left corner, we actually find that there's a lot of disagreement among the models, and therefore those specific technologies are much more in the corner of determined by the model, and then in the corner of determined by the climate target. So we know that renewables as a whole needs to increase rapidly. What kind of technologies exactly are chosen is a bit more difficult to get out of the models. Still, the overall story is quite robust now. And so simply based on this type of work that Mark did, we now know the robust story of dealing with climate change. And this simply comes from, if you look at the outcomes of the models. And so first of all, any scenario that stays below 1.5 degrees is first of all limiting demand, either by efficiency or by lifestyle change. If you don't do that, then you have to do so much work on the supply side that at some point it's simply unattractive. The second part is that renewable energy is a very important part of any mitigation scenario. And that's simply because renewable energy became so cheap over the last decade. Solar and wind are now almost as cheap as fossil alternatives. And so that means that in the electricity system and in industry, you would really like to use as much renewable energy as possible. If that is true, then it's also very attractive to electrify end use. Because then you are benefiting from that renewable potential. So use heat pumps in buildings, use electric cars in mobility. But it's not the whole story, because you can't use only renewables. There are moments that the sun is not shining and there's no wind. And so you need system integration, you need potentially some backup power plants, which could be bioenergy based or nuclear power based or carbon capture and storage based. And then there are also applications where electrification doesn't work because you need very high temperatures or in certain mobile situations like the air traffic. And that means that you also need to develop some other alternatives, which could be hydrogen or could be fossil fuels with carbon capture and storage or bioenergy, which needs to be developed as well. Reforestation is part of a robust solution, simply for the negative emissions. Developing other negative emission options is part of a robust solution. We need to reduce also the non-CO2 emissions. I've been not talking a lot about that, but it is things like methane and N2O. They are hard to reduce. Actually, methane and N2O, we more or less have technologies to halve their emissions. We don't have the technologies to bring them to zero. Methane is always related to livestock like cow, and we can find some ways to have stables or to reduce these emissions or give different feed, but they don't go to zero. And that means that if we want to go really low on the non-CO2 gases, actually diet change might be an important part of the solution as well. And it's maybe not a crazy solution, because if you look at the amount of meat consumption that is recommended for health reasons, that's about a third of the meat consumption that we are eating in OECD countries at the moment. And so there is a win-win situation here. We can improve our health by eating about a third of the meat that we're currently consuming in OECD countries, and at the same time significantly reducing greenhouse gas emissions for a very hard to abate source of emissions. Yeah, so we know a few things about scenarios that meet climate targets. Among others, that we have to get rid of fossil fuels. There are some scenarios where you might have a third of the fossil fuels left. If you're really optimistic about negative emissions and carbon capture and storage. But in almost any other scenarios, fossil fuels have to go to zero. And so that means in all cases, a very strong reduction. And it also means that we need a clear vision about the future. If we just look at my own country, the Netherlands, we still don't have a very strong description, very clear description of how the energy system would look like in 2050, which makes it much more difficult to make decisions about how much hydrogen do we need, or how much electricity, how is the electricity system going to look like. And this is not very far into the future, 2050. So it's important that we develop those visions. This is actually the last slide, and it's trying to emphasize the most difficult part actually of climate policy at the moment, which is not technology solutions or the pathways that we need to choose in terms of technology solutions, because we actually know those. The most difficult part is actually the distribution. And what you see here on the left is the total CO2 emissions of a few countries, the emissions per head, the second row, and the cumulative CO2 emissions. How much have countries contributed in the past to climate change? The first country that is there, and that's the first column, is China. And China is now responsible for about a third of the global emissions on its own. And the second country in that is the United States. The United States, the next two countries are actually India and the EU. And both the United States, India, and EU are around 10% of global emissions. But the emissions per head differ enormously. The United States is about 2 or 3 times the global average. India is a factor of 10 lower per capita than the United States, and the EU is in the middle there. And then if you look at historical contributions, again, India is nothing compared to the United States. So this makes us puts us in a really difficult situation. And so we need emission reductions in countries like China and India to meet the climate goals, simply because they are now such an important part of global emissions. And at the same time, it's very clear that these countries also have a legit position when they say, yeah, in terms of emissions per capita, we're way lower than you. It's not our turn. And moreover, it's not us that has created this problem. And so this is already slowing down those climate negotiations for a very long time. And this is the solution that we really need to find in the next few years to be able to move forward. And that's why climate justice is now so important. This is what I wanted to share. This is actually the summary. We are in a very important moment in time. The carbon budget is almost depleted for 1.5. It's really low for well below 2. And we have this huge emission gap. At the same time, there are positive messages as well. We have these technology breakthroughs. Renewables are now so cheap that they are competitive against fossil fuels. We have this electric car option. We also have the net zero targets of different countries, which is important. We have an organization like the IEA, which was created to make sure that the fossil fuel interests of OECD countries were taken care of. That same organization has turned around and says now we are in favor of the end of fossil fuel. And also the financial sector is changing. And so there are these dire messages. There are also some things going for the better. And let's see in the next decade where we can make this change. Thanks. This is what I wanted to share.
Well, thank you very much, Detlef, for this tour de force, the ins and outs of mitigation modeling. I'm sure there are many questions. Which is raise. Okay. I think you're the first.
So I was wondering, the IPCC report is updated like every 6 or 7 years, and the Shared Socio-economic Pathways are currently about 10 years old. Do you know, by your knowledge, if there are any plans to renew those as well?
Yeah, actually, we have just released new GDP and population pathways. We published them in early February. We're now running the land use and emissions energy scenarios again, and we hope to have results of that available early next year. Also, because we need to provide emission pathways for the large climate models next summer in order to be able to have new climate scenarios for the next round of IPCC. The next report of IPCC is going to be published in 2028. So we're exactly busy with doing that. And so GDP and population pathways are already available again, and energy and land use and emissions before next summer.
Excellent. More hands? Here, yeah, that's Jan.
My name is Ernst Kuiper. I work for Milieudefensie. I was part of the team that sued Shell. I have a question, and by the way, one of your PhD students, Lisette van Beek, was an expert on our site. So thanks for allowing her, I think, about 2 or 3 weeks to write an expert statement. I have a question about cost effectiveness in integrated assessment models, which was kind of important for our court case, because, well, to put bluntly, integrated assessment models, at least the way I understand it, calculate the cheapest way to stay within 1.5 degrees. And the results point towards the land sector and the coal sector having to reduce by far the most until 2030, in the order of 75% reduction to fully CO2 neutrality, while the oil and gas sector only needs to do about 10 to 20%, or in terms of reduction by 2030. And I was wondering, well, first of all, is that right? And second of all, for a court case, other principles than cost effectiveness were more important, like CBDR, according to the Paris Climate Agreement, the precautionary principle. And I was wondering to what extent these principles are actually included in integrated assessment models, and if not, if they will be soon. By the way, I will elaborate more on my question during my talk this afternoon, during my 5 to 10 minutes talk this afternoon. Sorry.
Thanks. Yeah. So first of all, yeah. So Lisette already had finished her PhD thesis, so we really have to thank her for. I was in contact also with her while she was writing, helping you guys. And it's true, more or less, what you're saying, and that's partly because the last decade, the first question that was on the mind of people was, is it possible to reach these climate goals? And so we were we were mostly absorbed by trying to find efficient ways and different pathways to reach these climate goals. And they're not only the cost optimal scenarios, but many of them are cost optimal scenarios, and most of them try to look at the problem from the world as a whole. And so we looked into pathways that maybe had diet change in them, or more renewables and less renewables, but it was mostly focused on the world as a whole. And that has a problem. And we didn't, and that is related partly to coal. Coal is one of the major contributors to climate change. It, in terms of CO2 emissions per unit of energy, it's twice as high as gas. But then also the power plant that where we use coal has an efficiency that is maybe half that of a natural gas plant. So the amount of CO2 per unit of electricity is about 4 times as high for coal than for natural gas. And so if you tell the model, please find a solution for climate change, the first thing it does is to get rid of coal. It's a logical thing to do. But the model, what we didn't tell the model in this question is, but the coal is in India and China. The coal and the oil and gas is mostly in for instance, in Western Europe. And I already ended my presentation by saying there are good arguments why Western Europe, the US, need to do much more on climate change than India. And so even if it's most cost efficient in this world to really get off coal first, there are other reasons why we might want to tackle oil and gas more than coal, simply because of who is responsible and justice arguments. And yes, these have simply been not as taken up as strongly as maybe it should have been, simply because we were absorbed a bit with a different question that we were trying to answer. And this is something that we need to do much more. Obviously, there's another route as well, which is trying to pay India to get rid of those coal power plants and maybe invest ourselves in renewable alternatives in these countries. But clearly, just reducing coal mostly in India and China would not be the fair way of reaching climate goals. And so the principle that you refer to that is really at stake might not be the precautionary principle, because that's maybe already taken care of by these ambitious climate scenarios, but it's mostly that principle that's also in the Paris Agreement that says we have common but differentiated responsibilities. And so both the climate treaty itself, but also Paris indicates that it expects rich countries with more capacity, with more responsibility to do more than poorer countries. And so, yeah, it is a problem in the current integrated assessment modeling literature, and we need to focus now on trying to address that issue.
Okay, good. Question here.
Thanks, Detlef, for the great presentation. My question is on the NGFS version of the IAMs. They have a big data set out, phase 4. What I don't understand is how you go from IAMs to downscale country-specific indicators. Can you speak to that?
So most of the integrated assessment models have regional differentiation, simply because it's important aspect of the problem, even more than maybe was appreciated by IAMs given the previous question. But for instance, image has 26 world regions, but that is not the country level. And so because people are interested in country level data as well, we have these downscaling rules. And so there are these little algorithms where we use existing historical data of countries within a region, and then some assumptions about how you would downscale that regional data to the country level. It has to be consistent with the country, and so you could assume that all the countries within a region may be reducing their emissions in a similar way, and so you could start from that. So you could say maybe they converge, but there are these algorithms that you can develop then to downscale the regional data to the country level. It might be useful in the context of trying to look still with a global perspective to how this might play out for different countries. I think you have to be quite careful not to interpret it too strongly, because it is downscaled data in the end. It's not really the country itself. And so if I have to say something about the Netherlands, I rather go to a model that is really about the Netherlands than to take downscaled data from an integrated assessment model.
Thank you.
Yeah. Oh, let's take a female and then
For negative emissions, you mentioned a disadvantage, namely that there's a temporary temperature overshoot. Why does that happen?
So we have a carbon budget, and the carbon budget of 1.5 degrees is now 250 gigatons of CO2. If we are using negative emissions to allow ourselves to not reach net zero in 2040, but in 2050, and then by 2050, we would have emitted more than that 250 gigatons of CO2. Let's say that we have emitted around 400 or 500 gigatons of CO2. And that means that in terms of temperature, the climate would already be at 1.6 or 1.7 degrees. Then we luckily have these options of trying to take CO2 out of the atmosphere again by energy CCS or by afforestation. And so we can go back to that carbon budget of 250 gigatons of CO2, but we will have a period where the temperature is 1.6 degrees or 1.65 degrees, and then we go back to 1.5 degrees. How dangerous that is actually also something that we're now going to spend more time on in research. We know that some of the climate impacts are reversible. Some of are not so reversible. So potentially climate impacts on crop yields, they are reversible. When we go back to lower temperatures, the yields will negative impacts will disappear. But for sea level rise, for instance, that is not reversible. That's such a slow process that you have. We will see a legacy of that period that was warmer. Biodiversity loss is something that is not reversible, and so this negative emissions are blessing in disguise. They have we will need them anyway. It's the chance that we stay below 1.5 now is next to zero. So we will have to go there with some form of overshoot, but hopefully the limited amount that is possible.
Great. Just before I give it up to the next question, here, I hear a lot of optimism on negative emission technologies, but currently I think we have 0.0002 gigatons per year from these novel technologies like DAX and BECCS, and we need to scale that up to 3, 4, 5 gigatons per year. I mean, how bullish are you on this scale up?
Yeah, so this is to some degree also possible danger of accounting with them. So technology-wise, afforestation is not the most complex thing to do. Technology-wise, having bioenergy and storing CO2 under the ground is something that can be done. How much we're going to use that, we don't know yet, and so it is important that we don't make ourselves too optimistic about the opportunity to do this, simply because we take a very high risk. At the same time, as the pathways are trying to show, and for 1.5 degrees, there is already no pathway anymore to reach 1.5 without some form of negative emissions and overshoot. And so the important message is try to limit it as much as possible, and at the same time do develop some of these technologies because we need them. And there is this pathway between what the Greek would say, Scylla and Charybdis. There are these two dangers, and we just need to find this pathway in the middle.
Okay. Thanks, Aaron.
So firstly, just a question of clarification. Did I hear you right saying that the remaining carbon budget for 2 degrees on current emissions trajectories in the absence of negative emissions technologies would be 2036?
Yeah, so this was 1.5 degrees, huh? And so the calculation is simple. IPCC starts with 400 to 500 gigatons of CO2. In the Working Group 3 report, this was revised to 400 gigatons of CO2. If we take out the 150 gigatons of CO2 that we have already emitted, you're left with a carbon budget of 250 gigatons of CO2. That's about 6 times the 40 gigatons that we emit every single year. And then you can calculate, it's a straight line if you take a straight line, from now to zero, then it's twice this 6 years, because on average so it's 12 years. So from 2024 plus 12, you end up in 2036.
Thanks, no, that's helpful, thanks. So the other question was, so there's energy demand in our economy is linked to economic growth, or the other way around, right? Economic growth is pretty much scales linearly with energy demand. So do you model any scenarios where we reduce the rates of economic growth, or actually go negative with rates of economic growth in some parts of the world?
Yeah, so in principle, I don't think that economic growth and energy need to be as linked as they were historically, and that's simply because of that difference that I, for instance, already showed between the United States and Japan. there's a factor of 4 or something like that in efficiency between these two countries, which simply based on technology choice and lifestyle. And so you can have exactly the same amount of GDP per capita and use 4 times as less energy. And so if we are, as humanity, go for very high efficiency technologies and to lifestyle choices that can create wealth, but much less intensity, I think it is possible to stabilize energy use for a long time or even go down. And that's also, for instance, emphasized in scenarios like the low energy demand scenario from EASA, LED. Yeah, we also explore alternative options. And so there are clearly also proponents of saying, yeah, maybe we are rich enough and we can go down on income levels as well as a possible solution to climate change. And so as part of the SHAPE project, for instance, we did develop these degrowth scenarios. The IAMs are only partly useful for that. It's relatively easy in the model that I have to bring down GDP and see that emissions go down. The real questions that you need to deal with in that case is how to have an economic system in such a situation. And so our tax systems are now based on a certain economic expectation. Our pensions are based on economic growth. So we first of all need some macroeconomic models to test out how would you organize economic systems in a situation of decreasing GDP. And it's probably not impossible, but that is, I think, a more interesting question than running an integrated assessment model with a decreasing GDP pathway. We still do it simply because our models are not only there for science reasons, they're also there for simply giving credibility to certain solutions. And simply the fact that we have run such a scenario makes it part of a discussion. And I think that by itself, the discussion is a valid discussion to have.
Very good. Anything? Yeah.
Just to follow up a bit on the inequality question of like who has to reduce how much. I have also seen some literature that says that in the current IAMs, the future predictions of various regions are actually based on the business as usual, and the inequalities will persist. So that if you that the kind of the GDP increase predicted for Africa is like very low, so that we actually will still increase our GDP much more than they, and the same for energy use and resource use, etc. So is this something that you plan to address in the update of the models?
So the reality is that we have created a world with enormous inequality. And so if you simply plot GDP of different countries per capita, you see this huge difference between the rich countries and the poor countries. So what we actually do in our scenarios is that the poor countries grow much faster than the developed countries. And that's simply also what standard economic theory would tell you normally, that if in a situation where we have equal and normal markets working, that there would be a reason why developing countries would grow fast. That's happening in our scenarios. We have the inequality scenario, this SSP3, and there the amount of convergence in relative terms is actually equal to what happened historically. Any other of the scenarios that we calculated, we have developing countries growing faster than happened historically in relative terms. But that means the gap is so large that in absolute terms, actually, that difference is still even increasing. If we have Western Europe growing at 2% per year, and we have Africa growing at 8% per year, but from a much lower level, then for a while, even in that situation, the absolute gap is not decreasing, it's even increasing. And so I don't think we are extremely pessimistic in our scenarios. We're actually very optimistic. We are more optimistic than occurred historically. But the matter fact of the matter is simply we have created a world that is so enormously unequal at the moment that it's really hard to in the future with reasonable assumptions to make it more equal. And again, for India, for instance, so I don't know whether you refer to a specific publication, but the Indian negotiator recently published an article where she's pointing to this, and she's pointing to the absolute differences between countries and criticizing the IM projections. And for us, we felt that we had to do something that was not completely unreasonable, that therefore taking already economic growth rates for developing countries that are much higher than developed countries and much higher than historically occurred was what we thought was the most optimistic thing that we could assume. I guess that we also soon will calculate deliberately scenarios where we have income convergence globally, but I think the world is far away just from a situation that something like that would happen. And so, and when I said income convergence, then income convergence even in absolute levels.
I wanted to rebound on what you said regarding giving credibility to a specific scenario. So you said like also model like when talking about big growth, that if you do like simulate some of these scenarios, it gives credibility to it. And regarding then the negative emissions that were mentioned before, I'm always kind of wondering how do we both accept that, okay, we will likely need to do some of this, so we need to look into how are we going to do this, we need to model this, and I think it also applies to other things like more geoengineering directed things, but how do we both accept this and model this in our models while avoiding giving the tools for instance, the oil industry to weaponize this, to be able to, you know, like explain why they can go on with business as usual and in status quo, and why they can still continue to go for oil in the next 20 years while investing in CCS. So,
I think it's a very good question. So it's in this field, you can be a naive objective researcher, and at the same time, you have to realize that it's used to advise policies, and therefore what you do is not without consequences necessarily. And what I try to do on this negative emission story is to try and emphasize both points, which is it is something that is useful and what we probably need to use, and at the same time it's not the main story. And so in the current policy scenario, when I was pointing out that it is more or less stable emissions, that means that we are emitting 40 gigatons of CO2. In the next 80 years, in this century, it would mean that we emit 3,000 gigatons, more than 3,000 gigatons of CO2, if we just continue as we are doing today. If we want to stay within that carbon budget of about 400 gigatons of CO2 or 250 gigatons of CO2, the main story is simply getting away of positive emissions. We need to get to reduce positive emissions with a few thousand gigatons of CO2. The negative emissions can at most contribute maybe a few hundred gigatons of CO2. And so above all, the main story is getting away of fossil fuels and really reducing fossil fuels, even in the most optimistic scenario for fossil fuels, by 80% or so. And so that in the short term, that is simply the main story. That we need some negative emissions at the same time should not be an excuse for having that story at the same time. So that's what I try to do, to emphasize also the main story, getting rid of fossil fuels, while at the same time it's important to also have some negative emissions.
Okay, Detlef, I know you have a meeting with the climate negotiators, so I don't want to keep you any longer. Thanks very much for the talk. Thank you,
Thanks.